When I say electricity, we tend to think about the stuff that powers computers or lights or heaters. And when I say magnetism, we tend to think about compass needles or maybe the things that stick to fridges, or possibly the elements of motors. But relatively recently in human history, we discovered that these two things, electricity and magnetism, were actually part of one thing called electromagnetism. And this theory defines nearly every interaction we ever experience. Electromagnetic forces are why I don't fall through this floor. They describe all of chemistry and the interaction between all materials. Electric fields are what make up light, X-rays, gamma rays, Wi-Fi, infrared, television, radio signals. Electromagnetic theory warned us about relativity. It's how we first discovered the existence of relativity, and it also led to the discovery of quantum field theory, which is our deepest theory of stuff, light, matter, everything. Every touch, taste, smell, and sight that you ever experience is coming to you courtesy of electromagnetism. But of course, that's a very modern realization. It took a very long time indeed for us to understand that all these different aspects of nature were in fact coming from the same fundamental principle. In a sense, that's the real power of physics. It lets us take what look like a whole lot of different phenomena and combine them using one simple theory. So for example, with gravity, we discovered that the way things fell on Earth also explained exactly how the stars and planets wheeled in the sky. In nature, you see electrical phenomena that are very clear in things like lightning or electric eels, but the first recorded experiment that dealt with the discovery of electricity was in fact in around 600 BC. Where a Greek mathematician noted that if you rub amber and fir together, then you can create a spark. And you can also store on the amber what looked like some kind of property that would cause things like hair to suddenly repel itself. This is what we call static electricity these days, and this was the first discovery of how you could put a charge on an object. And this property that the amber got, that we now call charge, we now understand is a fundamental property that things can have in the universe, just like mass. So charge is measured in coulombs, which is denoted by a capital C. It can be positive or negative. That's different to mass, which can only be positive, and it's also conserved. So you can't create or destroy a net charge. So what's happening when you rub amber and fir together, you're actually moving some of the particles from one to the other, and so one of them is becoming, on average, more positively charged, and the other one's becoming more negatively charged. So the total amount of charge hasn't changed, but each item now has a non-zero net charge. And the reason we know that charges exist is that when things have charge, then they interact with each other. And the theory of how charges interact is precisely the theory of electromagnetism. Now there's two ways of thinking about electromagnetism which are almost equivalent. The first is that charges attract and repel. In other words, if I have two positive charges, they'll each experience a force due to the other one, and that will cause them to repel. Same if they're both negative charges, and you might already know that if I have a positive charge and a negative charge, then they'll experience a force that is attractive. And the second model is that charges make an electromagnetic field. And then electromagnetic fields cause charges to feel forces. So you can basically see that these two models are equivalent. In both cases, you have a force on one charge due to another charge, except in this second model, you've got a charge making a field, and then the field making a force. And so you just got this extra step. And so a perfectly reasonable question would be, well, why add this extra step? Why have a model that has this extra complication in the existence of these fields in it? And the answer is that in the long run, using these fields actually makes things simpler to describe. It turns out that if you don't have those fields, then you don't have such things as conservation of momentum and energy. Because these fields themselves, this actual field, carries momentum and energy. And when you have something like light or X-rays or Wi-Fi or something, that radiation is just this wiggling electromagnetic field, and that carries energy from one place to another. And so if we include that, then all the rest of our physics and the rest of our understanding is much easier to handle.